In this video, we will be discussing simple linear regression. After watching this video, you should be able to understand the concept of a simple linear regression model and know why it is used, build a simple linear regression model utilizing the least squares application, interpret the simple linear model, find a variance and standard deviation of the model, and find the decomposition of variance and the coefficient of determination. So what is simple linear regression? Simple linear regression is a statistical method that allows us to summarize relationships between two continuous variables. The objectives of this practice is to establish if there is a relationship between two variables. For example, we could test to see if there is a relationship between income and daily spending, wage and years of education, or height and weight. The second objective of simple linear regression is to utilize this information to forecast new observations. For example, we could ask, how does an increase in a person's income affect their daily spending? And use a simple linear regression model to answer this question effectively. To further understand this concept, we will be looking at the following example. The owner of Mama Leona's pizza restaurant chain believes that if a restaurant is located near a college campus, there is a linear relationship between sales and the size of the student population. Suppose data is collected from a sample of 10 restaurants located near college campuses. For the ith restaurant in the sample, X is the size of the student population and Y is the quarterly sales. The values of X and Y for the 10 restaurants are summarized in the following sample. As we can see, we have 10 values for X and 10 values for Y, as X represents the student population and Y represents the quarterly sales. Our goal is to determine the relationship between these two variables and hopefully find a regression model that comfortably fits these values. When we plot these data values, you can see that there seems to be a pretty positive correlation between student population and quarterly sales. That is, as student population increases, quarterly sales also tends to increase. If we draw a line through this model, we can see that a linear relationship does seem to be present. So we will continue to use simple linear regression to make predictions based off this model. A simple linear regression model utilizes the following formula. Y of I is equal to beta 0 plus beta 1 times x of I plus epsilon of I, where beta 0 and beta 1 are both coefficients that can be found utilizing the least squares approach. Epsilon of I is the term that is used to account for error. This term indicates that given a value of x as our input, our output value of y is within a certain range of error, epsilon, and we know for a fact that epsilon is somewhere between 0 and our variance. Given observations x and y for I between 1 and n, we want to find the values of beta 0 and beta 1 using the least squares approach. We do this by minimizing the following function. We can minimize this function by taking derivatives with respect to both beta 0 and beta 1 and setting both of these equations equal to 0. Once we set these equations to 0, we can use a system of equations and find the values for both beta 1 and beta 0. As you can see, beta 0 is in respect to beta 1. This is one method of using the least squares approach, but it is not the most efficient. Deriving this formula takes time, and the formula is a little bit complicated to use. A simpler method of using the least squares approach is by breaking it down into SXY, SXX, and SYY. As you can see, beta 1 hat is equal to SXY over SXX, where SXY is equal to the product of the differences between the actual and the expected values. And SXX is equal to the sum of the squares of the expected minus the actual values. We can now apply this to our example. We have 10 values for X and 10 values for Y, representing the 10 restaurants on 10 different college campuses. We know that X bar is equal to 14, so that is our average X value, and our average Y value, Y bar, is equal to 130. We were also able to solve for SXY and SXX. We know that beta 1 hat is equal to SXY over SXX, which we have through this chart. We know that SXY is equal to 2,840 and SXX is equal to 568, which gives us a value of 5 for beta 1 hat. Now that we have beta 1 hat, we can use this information to solve for beta 0 hat. By plugging in this information, we find that beta 0 hat is equal to 60. Now that we have our two coefficients, we can build a linear regression model. Our predicted y value, also known as y hat, is equal to beta 0 plus beta 1 times x. And if we plug in the values 60 and 5, respectively, we have our predicted y, aka y hat, is equal to 60 plus 5x, which is our linear model. We can now graph this model, as shown here, and use it to predict the future. For example, if we were to ask, what if one college campus has a population of 2,000 more students? So, for example, if x is currently equal to 1, our y hat would be 65. But if x was equal to 3 instead, our y hat would then become 75, which means if x increases by 2, our y hat increases by 10, which means an increase of 2,000 students leads to an increase of 10,000 in quarterly earnings for Mama Leona's Pizza. We can also calculate variance to figure out how well our function fits our data points. Variance is a value that describes how much a random variable differs from its expected value. Standard deviation is simply the square root of variance and can be used for many applications. We can estimate the variance by using the following values. Variance is equal to 1 over n minus 1, where n is the number of terms in the model, times the sum of the actual minus the expected minus the actual value squared, summed for each value of I. We can also break down the variance into 3 separate parts. The first part is the sum of squares total, which is known as SST. This value is the total variation of observed y values. The second one is sum of squares regression, which is referred to as SSR, which is the explained variation of observed y values. The third variable is sum of squared errors, or SSE, which represents the unexplained variation of observed y values. We can then use this decomposition of variance to find the coefficient of determination. The coefficient of determination is the proportion of observed variation in the y that can be explained by the regression model. As you can see, it is referred to as r squared, and it is equal to the sum of squared regression over the sum of squared total. It can also be calculated by taking the sum of squared total, subtracting it by the sum of squared error, and dividing it by the sum of squared total. The r squared value is usually very important because it helps us determine how well our model fits our data points. So, in review, we learned how to find beta 1 hat and beta 0 hat utilizing SXY, SXX, and SYY. This is done using the least squares approach. We can then make predictions on our model using beta 0 and beta 1. We also learned how to calculate the variance and the standard deviation, which is just the square root of variance. We also learned the decomposition of the variance, the sum of squares total, the sum of squared regression, and the sum of squared errors. We can use all of this information to find the r-squared value, which is also referred to as the coefficient of determination. This value gives us a good broad example of how well our data is fitted by the model.